It's actually a little bit funny because like when I first told my mother that I'm using this programming language called Python, that's how she pronounced that. So that's just directly coming from my mom's pronunciation of Python, and like I couldn't come up with a better name because I suck at naming stuff, as some of other developers do as well. So I first started OpenGL stuff back when I was studying engineering physics, and I used it for making small animations like simulations and stuff. And later, after the university, I started working as a 3D engineer at a CAD software making company. So I had gained a lot of experience back then, but it was the old era. I guess it was 2006 or 2007. So the whole industry was still at low ground. Then I switched to backend programming and web technologies. But in the meantime, I tried to keep up with the 3D as a hobby as well. And like 3 years ago, I guess we had these hobby hours in our previous company where we were like people were talking about cycling or chess or whatever their hobbies are, and I wanted to talk about 3D and OpenGL. It was roughly 2 hours, and I literally sucked at it. Like it was a total failure. I catastrophically failed because I thought that by knowing the stuff that I was doing, like OpenGL, mathematics, and SDL, and keyboard controls, space geometry, all of those things, like I thought that I can just kickstart people. And I was so sad in the end that there were people who were really eager to learn something, really eager to get started with 3D, but I failed them because obviously I realized that 2 hours is not enough to get people started, even for experienced developers, because there are a lot of new jargons and like glossary and concepts to be learned. So I wanted to create something that I can teach within 15 minutes. And also there was another challenge, like when I first had the idea of doing something in Python 3D, all over the internet, it was always the same thing. Like you cannot do 3D stuff in Python because Python is an interpreted language, and it will not just keep up with the frame rates and stuff like that. So I saw it as a challenge, and I get started with the ideas. Like I wanted to give people ability to whatever they want to create. I wanted to give them a playground. So my first philosophy would be it should be easy to start. People should see the results immediately. It should come with the defaults that make sense. It should be less verbose but extendable. It should be restricting, but it should work. There are a lot of libraries in the industry, like most of them like game engines or graphic libraries, and all of them are awesome, like Unity engine or all of them, like Godot or like whatever comes to your mind, from Ogre to IRR Lit, so many. But they are all verbose because they want to give the developers the ability to create some industrial level things or like games. So their learning curves are always high. Like you cannot just get started with them. You have to learn a lot of things. You have to learn how to set up a scene. You have to learn how to set up your controls. You have to learn at least some principles about the materials or projections or matrices. You have to learn lots of things with those. And also, especially thinking about the game engines, they come with so many dependencies on your system that I remember setting up Unreal Engine on my local. It took me like 2 or 3 hours to make all the dependencies as it should be. So even as I'm an experienced developer, it takes too much of a hassle to get started with all these libraries and game engines because they have so many features to give you. But I said, hell, I don't need those features. I just need to get people started. If people enjoy 3D stuff and get the basic idea how it works, they can just jump into more mature grounds but I can be the man in the middle to get people started. So that's why no experience is required. Was one of the philosophies of me doing this. So what can you do with Payton? These are things that you cannot do. Probably you cannot do extreme games or industrial level stuff like complex design softwares or like high performance applications like a complete physics engine. Those would be so hard to do because of their CPU intensive approaches. And Python comes with global interrupt lock, which is quite restrictive about the CPU usage. But what you can do is you can create small games. You can visualize your 3D data. You can do artificial intelligence research, like if you have an algorithm in mind and if you want to see your robot trying to find its way around the scene, like a pathfinding algorithm, or if you want to create a bot for some games and you have the basic idea, but you do not know where to get started, it's a good playground. You can test your 3D algorithms for building meshes or like splitting meshes, objects in 3D, or you can do basic modeling applications or tools, or you can do some tools programming, like if you want to build a game and you come up with your own map format and you want to create some map editor or character editor or something, you can still use Payton on those because they are not too much CPU intensive, and Payton tries to cover your graphics card. So yeah, let's get started. So for this, I'll just, okay, where's my terminal? And let me just zoom in a little bit. Somehow today my keyboard shortcuts doesn't seem to work. I don't know why. So I'll zoom in like an idiot. So I created a virtual environment and I just say pip install Payton. So the basic requirements for Payton are like OpenGL drivers on your computer and SDL libraries on your computer. The rest, like Pillow and NumPy, they just on Windows machines, for instance, they just come binary, so it's not much of a hassle. The requirements are still quite small, and that's all you have to do to install it. And to run with it, I just drop to IPython. So I just import a dummy scene. I create a scene, and I just run it. So I have my window here. So it's this easy to get started. Payton will create a scene for you with reasonable controls, like if you right-click and drag, it will rotate. If you middle-click and drag, it will pan the scene. If you press H, it will open up a how-to-use window here, like zoom in, zoom out, or change the camera mode to perspective or orthographic. If you have any clocks in the scene, which I will describe a little bit later, it will start the scene, hide and show the grid, change the display mode, or if you have multiple cameras, just switch between the cameras. And these are the basic functionalities that you can do. That's why I mentioned, like, you do not have to deal with any of the things. Like, you do not, here in the scene, you do not have to code a camera because it comes with a default camera. You do not have to code any SDL related stuff because Payton already creates the SDL window for you, along with the mouse and keyboard controls, with multiple camera modes. So everything that you need as a playground comes already with Payton, which is restricting, but that was the basic idea. Like, if you feel that Payton is restricting you, then it's probably time that you move to a more mature or more flexible environment. But at least if this is enough for you, then you can stick to it. There are still so many things that you can create. For instance, as the final demo, I will show you a small Minecraft-ish environment, a multiplayer block putting game. Like you can do so many things even with this state. So I just quickly quit this terminal and switch to my VS Code and switch to presentation mode. All right, so for this session, instead of wasting your time by writing a lot of keyboard stuff, I will go through the examples that you can also find within the Payton repository, which I will also share the link in the end. So the reason that I have so many examples is I hate to read documentations. Whenever I see some huge documentation of an API, I just scan through the documentation and try to find code pieces that I can cheat. So instead of creating a huge documentation and try to tell about everything step by step, I thought that just giving the developers some basic codes to cover all the features by themselves would be much more explaining than the documentation itself. So I'll just start by the basic scene basic scene example. So as you will see, the code itself is quite commented. At least I try to do it that way. And the code itself, the library itself, is heavily type hinted. So your editor will pretty much guide you through what you should use. For instance, if I just come back a little bit and say that scene, like for every action, the editor can give you the whole information that you need about what you can do with that action and what it is used for. Also, there are examples for all of those. So back again to this. So let's start it with this rather a complex example, but I can quickly reduce the complexity of it. But before doing that, I'd like to show you this. So this example simply creates a ground with a texture, a cube hovering and a cube on the ground, and another wall behind the scene, and a default light. And the light is capable of casting a shadow on the scene. So if you just start hit the space button, the light begins to rotate around these cubes, and you see that the shadow is dynamic and is cast actively, and you can just move around the scene. And the magic that does that behind the scenes is, if I have to explain step by step, I have a scene, and I set the scene's shadow quality to high. I have a little function here, which I will come later, but Payton library comes with predefined geometries like cube and plane. There are much more geometry items like you have line and cube and cylinder and MD2 files. I don't know if you are old enough, but I grew up with playing Quake and Quake 2. MD2 is a format that comes from Quake 2 ID2 engine. It's their object, like moving object formats, mesh, a particle system, a matrix plane, a ragdoll, a sphere, and wavefront object format, which mainly almost all modeling tools like Blender or 3D Studio Max can export your objects. So that means whatever you design or whatever you find online, there's a huge archive of wavefront objects. So from the geometry, I import cube and plane, and I have a scene. So I create a cube. By default, the cube's sizes are 1, 1, 1. and I give it a position. It's simply a list with X, Y, and Z coordinates. I create the ground as a plane. I create a wall as a plane, and I rotate the wall so that it's going up, not like flat, and give it a position. I changed the default light's position, but this is not mandatory. I created another cube here. This example shows you two different ways of creating a cube. The first way is just tell it nothing, or you can just give it like width is 2, depth is 2, and height is just 1, you can say, or give it a float. And the second example, you are able to create a corner from this location to this location, so it might be easier for some people to define those. So if you want some cube to fit exactly to an empty space that you know, it's where you do that. And here is the tricky part that makes the motion, clocks. So one other concept that I failed to describe to my friends, especially to the beginners, was threads, like multi-threading and concurrency. So I thought that instead of making people creating threading models, I can create clocks. Some game engines also work with the clocks, for instance, Unity engine. So basically, clock has a name, has an interval in seconds, and has a function, which means that when you create a clock, every this second, this function will be called. Making it with seconds is the good part, but because you are now able to control the frames, like the speed of the motion. And when the system calls this function, it calls with two parameters, the period of the clock and the total amount that has passed since the beginning of the animation. So I have a texture file, a JPEG image here. I assigned the texture file to the material. This is kind of redundant as well, like it can confuse you. But basically, I'm just giving the barrel texture to the models. Then in the end, when I defined my cube, my ground, my wall, I add those to my scene by using the add object command. So add object wall, add object cube by corners, add object ground, and set the scene's grid visible to false so that we do not see the grid when we first started, and just run the scene. And when we run the scene again, we just shrink the size of this, and if I hit the G button, you'll see the grid is there. And also other keyboard shortcuts like W, changing the view type. So this was rather a little bit of complex example. And as another example with the motion, I guess this is still redundantly complex. Yes, this is a better example, I suppose. So I again have my scene. I create a sphere. I add it to the scene. I say scene that please track this object. So keep your eyes on the object, not at the scene. I resize the grid. I create a plane again for the ground. And this time I create two clocks. One is for projectile motion, and the second one is for logger. Apologies. This was one of the early examples that I have created. And I have my parameters here, the launch angle, gravity, initial velocity, and I coded the projectile motion function here. And I coded a logger here, which will basically debug the ball's position in the scene. So here we have the example, and I hit space, and in the logger I can see the ball's position relative to time, and the ball is here. So when we return back to the code, it's roughly, I don't know how many lines, 75 lines. And we can just delete the logger and just remove it from here as well, because it was just something redundant. What else we can get rid of? Well, we have the scene, we have the ball, we do not need this. I don't want to track its motion as well. I do not want this information box as well, so we are just getting rid of the redundant codes inside it. So I have a simpler screen now, and it's just moving. The library itself has a lot of features that you might need while doing some stuff. For instance, one of the things that is quite tricky in the OpenGL or 3D universe is to apologies, is to be able to pick stuff, because object picking requires a lot of mathematics. You have to know the projection matrix and the view matrix and the location of the cursor. So you simply convert the camera's inner matrix to the world matrix, then try to figure out if you have a ray and if that ray hits any of the objects in the scene. But instead, here in this example, if I come back to presentation mode again, I have a cube. I literally don't need the info box. I can just delete the info box for now. So simply speaking, I have a scene, and scene can get an onSelect callback. And if you define a method with a list of objects, when you select something in the scene, this method will be called by the scene. So that's just a callback. So here I create 10 cubes at random positions, at random colors, and I add them to the scene and I run the scene. I guess it's pretty straightforward and quite a small piece of code. And here in this example, I have a lot of cubes, like 10 cubes, and just clicking on the cubes selects them in both of the camera modes. So to do this in the beginning, like I just have a cube and I just have a function, and I just want to like print the selection. I have a scene. I add the object to the scene as cube, and scene has onSelect callback as selection. So this is all you need to do. Oops. Where is my window? Here, I didn't run the scene. So basically, when you run the scene, you get a cube, and when you click on the cube, it just prints the list of cubes selected. So that's why I wanted to create something so simple. Like all you need to do is just create the scene, add your object, and run it. Define your callbacks so that callbacks can handle your back, like get your back there. Another good example is, like, I literally love showing this to people. If you are following me on LinkedIn, probably not. This is something that I occasionally love to share just to get some attraction. This is rather a little bit long, but I'll describe it later. So this creates 10,000 particles in the scene, and all of them are at the same location right now. And when I hit the animation, you will see this awesome explosion effect. And the frame rate is, even though my screen is quite large, isn't dropping below 60 frames per second. And after the animation, it's actually higher. So how does this animation work? This is an approach that is like my previous examples, for instance. Let's return back to picking. This is not object-oriented. This is just purely procedural. So I just code everything inside a single file, no patterns or anything. But here in this example, this is a little bit of tidier approach. I extend the scene, and I created this particle demo application from the scene. I have my arguments here. I call the super. So particle system is one of the properties of one of the features of Payton. So basically, it gives you a cloud of particles, and you just simply add points to the particle. It's simple as that. So I create a particle system, and I want the particles to look a little bit of orange color. This is the RGB codes of orange. And I also I add this particle system. I guess I should have named this better. Particle system of explosion. Yeah, as I mentioned, I suck at naming stuff, so I warned you. This info box is a user interface element. You can quickly create information boxes on the screen. This can be an alert box or like anything you want. You just define the left position and top position on the screen and give it a label, and it will just print it with a close button under. This rather a little bit of hot like heads-up display, but actually I could have made this another info box. I guess I was lazy. But this is simply another label on the screen with a position. And I create two clocks here. The first clock is to animate the scene, and the second clock is to show the frames per second on the scene. So in the beginning, I just generate the particles, 10,000 particles. I give them some data. So particle cloud is a little bit of special example because I thought that whoever uses this particle cloud might need some extra information, like it actually gets a keyword arguments, and when you add some particle, you can assign meta variables to those as well, which means each particle can store information. And in this example, our particles store the information of, where am I? The information of velocity and orientation and their launch angles. So I create particles so that they will just spread all around the scene with different velocities and different orientations. And my heads-up display just shows the scenes frame per second. I do not have to use a heads-up display, but rather I can just simply print it to console as well. Scene comes with FPS variable already inside, so scene is capable of updating its FPS counter, so you do not have to do that yourself. And the animation itself goes through 10,000 particles, and for each particle it calculates the next position and just refreshes the whole particle cloud. The reason of this refresh is like setting the vertices is not enough to get things rendered because of the performance reasons. So in the end, when you update all the things that you need to update, you have to apply it by refreshing it. Refresh just sets a flag as needs update, and the whole system will update that object in the graphics card. And that's the good part of it. Like in 3D, if you want to achieve something that looks like a particle, like a real particle, actually all of these particles are squares, and those squares have a texture on them, a PNG image, which is round. And in the graphics card, there's a shader code that always makes these squares to face to the camera. So these squares are actually following the camera location at all times. That's why it gives you the illusion as it's a ball-like particle, but actually it's just a flat surface. And that's why I had to use OpenGL with a little bit of a newer version so that I can just put all these kind of calculations to the graphics card, and Python itself as the interpreter doesn't have to deal with any of these extra calculations, but it will just deal with the particle calculations, like the positions of the particles only. And the frame rate here doesn't drop below 60, which is quite good in this case. And in the beginning and in the end, it reaches up to 300 frames per second, which is, I believe, awesome for an interpreted language. And so, if I return back to the examples, and sorry for boring you to hell with the examples, another good example is another good feature of Payton, I can tell, which is giving me headaches, but at least the people who uses Payton is quite happy with it. So I'm happy with the headache. But if you are willing to contribute, this is one of the key features that I need some help with. It's basically a graphical user interface support. In Payton, you can create a graphical user interface like a window, and you can add buttons and edit boxes to this window so that you can create some actions out of it. If I run this example, you see that there are two edit areas here. The first area is the cube size, like 2, 1, 3. And when I click on this button, it creates random cubes with that size. And this is the multi-line example. So you can actually write something long, and it's performing not that bad. There are still some performance issues because with every keystroke, I'm actually generating a texture and image there, but it works. And the frames per second is still bearable with the interface. But I need to add more interface elements like checkboxes and lists or scrollable windows. So that's where I still need to improve the things, but at least this functionality seems to be enough for many people. And to create those, I wanted to create something like, I hate to code with Qt or TK or other libraries because there are also two variables to do some stuff. Mainly, they all either occupy all the space, or they either just, you have to create a lot of codes to get things rolling. So I wanted to do something quite simple. I wanted to give it some simple arguments, and actually many of these ideas, like width, height, or the alignment information, is coming from my university years. Back at the university, I heavily worked with a great programming language called Delphi. Honestly speaking, I really like Pascal, and still to this day, I sometimes code with Lazarus, free Pascal. I like its what you see is what you get approach, and its designer. So I wanted to do something really as simple as that. Like, even though we do not have a interface designer here, it should be quite easy to do some stuff. So I have a window, I have a button, edit box, another button with extra parameters to show their sizes, and callback events, and another free text edit box, which is multi-line. And I add those to my window. I create cube button, cube size edit box, frames per second text, and free text. Then in the end, I add this window to my heads-up display, which I guess in the beginning I created a heads-up display and I added it to the scene. This heads-up display is just some kind of a meta object. You do not have to worry about it at all, but if you want to print something two-dimensional on the scene, you need heads-up display. I guess I should be moving this to the bottom. Anyways, somewhere here, maybe, yeah. So every button has an on-click callback, which is a very simple method, and it just generates some random integers. It gives it, it uses the object count to name the object in the scene, and it just puts the cube into the scene with given width, depth, height parameters, and these parameters are actually coming from the edit box itself. So edit box has onChange event. So when you change something at the edit box, it calls set size, and this just stupidly reaches the global, parses the given string, and sets the global variables. And that's quite stupid. Yes, there are a lot of violations in the examples. For instance, I shouldn't be reaching the global. That's a bad practice, but I wanted the examples to be as simple as possible so that people can just catch up with the idea. So instead of using some elegant codes here, I wanted it to be messy at the examples, but teaching. But that's not the same for the code base itself. And probably last but not least, one of the coolest examples is the Quake example. So here in the presentation mode again, as I mentioned, I come from an era where we played Quake a lot. So in this example, I thought that people might need to create some games, at least some basic like seek and find kind of algorithms. So to have the most of that experience, you want to see something that is looking cool, that's actually looking like a soldier on the scene. And for that purpose, there are a lot of formats, but one of the easiest formats for me to code was actually this Quake format, and it's quite suitable for an interpreted language because it's not CPU intensive, it's GPU intensive. It works like a GIF animation. I have every frame as an object, and I push those frames to the frame buffer. And for every frame, I just switch those objects in the scene, which gives you the illusion of a moving object, but actually it's not a moving object, it's just changing the frames. Loading that object is quite easy. Like I have the model file, this is just a file path, and I create an MD2 object with the file name. If there are, these models usually come with their textures, but the texture handling and the materials are handled automatically by this class itself, so you do not have to worry about it. So I create an information box at the user interface. I add a ground and I add my infantry soldier. I have some extra controller, which is, if I, this kind of complex, I know, but I apologize for that, but I wanted to do some interaction with the keyboard. But if you press up, it will walk. If you press down, it will die. And that's all. So before baking the animation, I just want to show it as this and run it. So I didn't bake the animation. What does that mean? So this file format comes with keyframes, not the whole frame set of the animation. So this jagged look is actually some important keys in the animation, and you have to fill in the gaps in this object according to your preferences. That's how this object format is defined, because back in those times, memory was precious, especially when you're creating an object and putting it into a disk. Just imagine that you are actually putting those objects into floppy disks, 144 megabytes, so it should be fitting those. So they just cut some corners there, cut some frames there, and thought that whoever programs to read this stuff is intelligent enough to fill in the gaps of the animation. So that's why we have the bake animation here. It simply says that for the walking animation, starting from frame 2 to 14, bake it in a way that between every keyframes, create 3 more frames, so that it's going to be, it won't be like this, but it's going to be smooth. And for that as well. So I just roll back this line. And when I run the same code again with baking, it takes a little bit of more time here. And it's kind of slower now. And I guess I just broke something before the demo, but I don't know what I broke. But anyways, yeah, demos and me, just every time something goes wrong. But at least you can see that the animation itself is not that jagged, and yeah, it's working properly now. And it's smoother now, and with the keyboard controls, I can make it walk or just die. Every object comes with some animations, but unfortunately, these animation names and the frame numbers are not standard. So whoever designs the object is free to name it in whatever way they wish. So it's up to you to print the animations like this and decide on which animation to use. For instance, if I use paint animation, instead of that, I wanted to use paint. I guess the frame size should be the same, so I shouldn't be having too much of a problem. And I'm waiting for it to build the frames. Actually, my window hasn't popped up yet. Maybe I did something wrong. I'm not sure. Just give it a second. All right, I guess I did something wrong, but you pretty much got the idea, I suppose. As I mentioned, there are so many examples for every feature. For instance, in another example, I have the object file. This is a waveform object, so it's an axis2, which is the standard monkey face Susanna from Blender, and it has the vertices, textures, etc., all the redundant stuff that you do not have to know. So basically, I create a scene, I create a plane, I load my object, and here I export my object, and I import the exported object to my scene instead of the original object. This is an example of exporting a mesh, like any object. It can be a cube, it can be a sphere, it can be this Quake example. Whatever you have in Payton, you can export it as a waveform object and import it to your favorite application. There's a very good reason for this, which I will shortly explain. But here is my Susanne. So the reason why I did this was another feature of Payton. So instead of just doing animations and cool stuff like that, you can also actually do something more productive. One of the things that I can show you is Payton comes with mesh tools, a tools library. So inside the tools library, I can show you. Yes, I have the line tools, which are extruding a line, rotating a line, or converting lines to meshes, and geometry tools like merging multiple mesh objects or subdividing an object. So with these tools, you can do more with Payton, actually. For instance, in this example, I have a line, and this line have vertices. They are like 3D coordinates in space, and they just make a line. And I rotate this line along the x-axis in 360 degrees with 20 steps. And that gets me an object like this. You see that, like, in the cross section here, you see my line definition here going to the bottom, to the 0 coordinate, and I just rotated this line 360 degrees with 20 different steps. To get something smoother, I just need to increase the steps like 60. And I get it smoother here right now with more steps. Or yet with another example, one of the things, yes, Extrude Line. I don't know if you have ever worked with 3D modeling tools, but extruding is a good feature. For instance, you have a square, and if you extrude a square in 3 dimensions, you get a cube from that. So that's the simple idea. Here I do have a line again, starting from the origin and ending in the origin as well. And I just extrude it along the x-axis. But my line is not totally square. It's a little bit artistic here. So the Z components of these points are going up. So I end up with an artistic mesh like this. I can also export this from Payton and use it in another 3D application. Or lines to mesh is, actually I should probably just run it. So I'm able to draw some kind of a building like this by giving it some information. So the information is, I have two lines here. The first line is the exteriors of the wall, like the edges of the wall, and the second line is the window line. And I tell Payton to connect these lines in a way that when Payton connects these lines, it just creates a surface between those two lines. So window remains a gap, and the rest is just created. And again, here for the roof, I have the edges of the roof in coordinates, and I have a rooftop as a single line, and I just connect this roof base to rooftop, and that actually looks like a real roof. So you can make Payton to create objects for you, not just animations. Okay, I have a glitch in my environment. In some cases, I guess the window doesn't pop up. So there's our home. There are, of course, like I try to keep these simple, but there are, of course, more expert, like more high-level examples as well. For instance, I have this JPEG image here, which is a grayscaled engraving. So I created this example so that I can create an engraving 3D object from this given image. It's currently building now, so I have to wait for this. It takes a while because it creates a lot of vertices. There it is. This literally takes time because it's, come on, just yes. It's built more than 2 million vertices, triangles. So that was the reason why we had to wait. But once it builds the object, Python itself is capable of just handling this massive object, because actually once it creates the object itself, it pushes the things to your graphics card, and from that moment forward, it's not at the CPU, it's just running on the GPU, and it's just taking almost nothing to render. So yeah, and when I render it with wireframe mode, I guess the word triangles are so small that it's almost impossible to get close. Or with another example, which are one of my favorite examples that I occasionally use to just get attention of the people, is the ripple example, which is simply a ripple generator. This is another example that I did to measure the, actually I'm using this to measure my interpreter performance, because in every frame is Python itself to change the vertices here. So this is a CPU intensive example, but It does well. I just want to increase the water size to 100 and see it in more detailed, which looks like this. So as you can see, with 10,000 points, the ripples are a little bit of, heavier to calculate now. So I usually use this example to improve the performance of my codes, but it looks cool. So this example is, if I have to show it, I have a matrix plane from the geometry library, and the core of this example is about the matrix plane. There's also a simpler example of the matrix plane. I guess that example was, let me check. That one, not motion, not that, not background, camera, no. Yes, this one. This is another example of matrix plane, which is something that you might use in visualizing 3D data. Basically, matrix plane is, when you define a matrix plane, you define the resolution of the plane with a fixed width and total width and total height of the object. And within this resolution, it creates a lot of points in space. And you can actually, within this grid, matrix plane comes with a grid. The grid itself is a two-dimensional array, so it comes with X and Y. It's too small probably for you to see. So matrix plane comes with a grid, and it comes with I and J and X and Y coordinates. So you can actually set the height of a grid point in space. So you define the Z property of all points in the matrix. And from these Z coordinates, the system just automatically builds the object for you. And in my previous example here with the ripple effect, where was that? Yes, with the ripple application. These are just not so important background information, like background color to make it look cool. Click plane is another feature of Payton for me to click, but this is also redundant because I already have a timer to drop some water to the scene. So the whole calculation is done with a clock, and the clock itself is iterating through these points, and from previous state to existing state, it calculates the next state of the grid and updates the grid. It's a rather complex example due to its physics, but as the metric itself is, there are a lot of questions. I will come to that. Yes, I promise. So I guess I'll just go through the questions here. Or yeah, I guess it's time to go through the questions because I've been talking for an hour.
Yeah. So thank you very much, Sinan. Just wanted to point out that this is a great marathon of presenting, and we have some questions.
Yeah, I can quickly go through them, quickly.
Yes.
All right, I'm starting from the top. Is it recording? I guess it's recording. So can I have multiple light sources? Yes, you can have multiple light sources, but there's a limit that you can have 100 light sources and only the first light source actually casts shadows. The other light sources currently do not cast shadow due to performance issues, but I'll be working on it. And what else?
There's
entity selecting or searching. Yes, it's possible. It's the example 07. I guess I should just git reset here. It's easier. So if I run this example once again, I have the scene and it's able to do casting and selecting the objects. It simply does it by defining an onSelect callback to the scene. And if you define an onSelect callback to the scene, when you click on an object or more than one objects are casted, then you will get them as a list. There's also some basic collision detection. Not a collision response, so not a fully featured physics engine, but at least you can see the colliding objects marked as red here and there. Or with a little bit of more detail, which the objects here, I remember, were broken. But there are two types of algorithms for the collision detection, and this algorithm just compares both of them. The red algorithm is faster, but not that accurate. The green algorithm is more accurate, but not that faster. Can you have more than... Yeah, you can have other light colors. For instance, if I return to the cube example here, I can just give a color to the light here. Let me just quickly do that. Initial light dot color is red, green, blue, and let's roll. And there is your red color of light. You're welcome. So that was, I guess, pretty much it. And I'm happy to get more questions also. But I guess we are, like, I already consumed a lot of your times, which I'm quite famous. I guess Jakub already knows this from my demos.
Yes. So thank you very much, Sinan. We have a round of silent applause for you. Well, muted applause because everyone's behind mute. So we are now getting into the next part of the Pyvo, and that is free discussion. So if anyone has questions about this, please ask. Sinan, how much time you have? You're staying with us?
I'm here.
Good. No, so hurry. Probably you will be able to still ask questions, and or / we can have just a off-topic, on-topic around Pythonish chit-chat for some time. Usually, if you leave, will we still be able to continue?
I don't know. But I think I should stop the recording now, right?
Yes.
Right. Thanks, Sinan.